Welcome back. In this video, we will look at the empirical rule, sometimes called the 68, 95, 99.7 rule. So this applies when we have a distribution that is bell-shaped. So we can often decide whether or not a distribution is bell-shaped by looking at a histogram or maybe a dot plot. But as a reminder, a bell-shaped distribution will generally have this shape. And so there's a peak in the middle, and this peak corresponds to the mean, but also the median and mode. So the mode, because it's the peak, so it's the most frequent value. The median, because there are just as many values below as above. And so the mean. So another thing that's nice to know about this bell-shaped distribution, and that relates to our discussion of standard deviation and measures of spread, is at some point in a bell-shaped curve, the curvature changes, and it goes from something like this to something like this. The point at which that change occurs is called an inflection point. And the way that that relates to the standard deviation is in a bell-shaped curve, we see an inflection point one standard deviation from the mean. So let's say that that point is right about here. Then I know that this distance, and if I had a scale down here of values, then the distance between here and here, that's one standard deviation. So if this is my mean, and I'll say mu, then this would be the mean plus one standard deviation. And it's symmetric, so if I go to the left-hand side, this point would be the mean minus one standard deviation. And if I know the length of a standard deviation, that's not going to change. I could actually go this same distance one more time, and that would be the mean plus two standard deviations, and this would be the mean plus three standard deviations. And that works the same going over to the left. This would be the mean minus two and the mean minus three standard deviations. The reason I point that out is the reason we call the empirical rule, the 68, 95, 99.7 rule, is because if we stay within one standard deviation of the mean, so that would be the mean plus or minus one standard deviation, we'll capture 68% of our data. And if we take the mean plus or minus two standard deviations, we'll capture 95%. And if we stay within three standard deviations, we'll capture 99.7% of the data. So if we know that something is bell-shaped, a distribution is bell-shaped, and we know where the center is, in other words, the mean, and we know its measure of spread, either the sample standard deviation or population standard deviation, we can estimate the amount of data that is within a certain range. So let me give you an example. So among men who are, I think 18 to around 25, we'll say, the mean height, so I'll say this is the population mean, so I'm going to use the symbol mu. The mean height is about 5 feet 10 inches. But of course, there's a lot of variety. And in fact, the standard deviation is about 3 inches. And there is a normal distribution among the heights of men, so a bell-shaped distribution. So if I look at this distribution, I expect it to have this shape. And this mean is the value that's right in the middle. So here's where the mean is 5 feet 10 inches. And if I look at one standard deviation from the mean, 2, 3, I'm just going to go ahead and draw some markers here and then I'll label them. So this would be the mean plus 3 inches, so plus one standard deviation. Well, if I add 3 inches to 510, that would take me to 6.1. And if I add another standard deviation, that would take me to 6.4, and another standard deviation, and I would be up to 6.7. So this is the mean plus 1 standard deviation. This is the mean plus 2 standard deviations, and this is the mean plus 3 standard deviations. When on the other side, if I subtract 3 inches, that would be 5.7. So 5.10, take away 3 inches. This would be 5'4" and 5'1". This is the mean minus a standard deviation, the mean minus 2 standard deviations, and finally the mean minus 3 standard deviations. So what does the empirical rule tell us about the distribution of heights of men? Well, it says that 68% of men who are between the ages of 18 and 25 are between 5'7" and 6'1". And 95% of men in this age range are between 5'4" and 6'4". And finally, almost all, or 99.7% of men are between 5'1" and 6'7". So these values that I'm writing on the outside of the curve, those depend on these two measures, the mean and the standard deviation. But the percentages for the empirical rule, those are constant, so that's why we can also call it the 68, 95, 99.7 rule. This works also for estimates if we have sample data, in which case we would be using X bar and S instead of mu and sigma. So in that case, your curve would be labeled with X bar in the middle, and then this would be X bar plus 1S and X bar plus 2S, and then lastly X bar plus 3S, and the same on the other side. But again, you want to check to make sure that you have a bell-shaped distribution before you apply the empirical rule. And sometimes you're going to have to calculate these two values so that you can label your curve and figure out the lower and upper bounds for these ranges that correspond to these various percentages. So let's look at examples of how we might use this. Kind of tie everything together from this chapter. So this is a table with values. These are the lengths of eruptions in seconds for the Geyser Old Faithful. So the first thing I want to do is calculate some statistics. Now this is a sample, so what I want to do is use my calculator. And in fact, I've already put this data in my calculator. I went to the stat menu and using the edit function, actually it's a different calculator. So a quick switch here. Stat, edit. So in the fourth column here, L4, I entered this data. And so now I want to calculate some of these statistics. So using my T84, if I hit stat and then arrow over to the calculation menu, that first option says one variable statistics, and my data is in L4. So I hit the second button and then the 4, and that populated L4 there. Now I hit enter, and I get a number of statistics here. So firstly, I have my mean, which I'll add here. That's X bar. X bar is 104. I'm just going to round to whole numbers. The standard deviation, so there are two values reported here. There is the sample standard deviation, so the symbol S, and the population standard deviation using the symbol sigma. Since this was a sample, I want to use the first value, 6.249, rather than 6.177. I'm also going to round this value to the uh, uh, to a whole number, and we're going to call that 6. Oh, I already had mean written here. Why don't we do this? I want to add variance. So range and variance are not automatically given from our calculator. However, if we keep scrolling down, we do find the minimum and the maximum. So the maximum value was 120, the minimum was 90. So that means that the range is the difference between those values, which is 30. And standard deviation is the square of, I'm sorry, variance is the square of standard deviation. So actually, I'm going to backtrack a little bit and say this was 6.249, and then I'll round at the 4th decimal place and say that's 1. So I'm going to return to my home screen, and to get variance, I need to square this value. So 6.2491 squared, and so the variance is 39. And again, I only kept the decimals because I wanted to get a more accurate answer when I squared. But here are the values that I'm going to use for the mean, the range, the variance, and the standard deviation. So next, I want to know the shape of this distribution. And so I'm going to construct a frequency table. So I know that the range was 30, and let's go for maybe 6 classes. So they'll have a class width of 5. My smallest value was 90, so why don't we go from 90 to 94, 95 to 99, 100 to 104, 105 to 109, and so the maximum is 120, so I need to keep going to 110, and then 115, and I'm actually going to need one more value. So this would be 114 and 119, and we'll have to have 120 to 124. So these are the lengths in seconds, and here we'll have the frequency. So in the 90 to 94 range, about 1, 2, 3, 4, and in the 95 to 99, I've got 1, 2, 3, 100 to 104, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, and 105 to 109. Let's see, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 110. I've got 1, 2, 3, 4, 5, 6, 7, 115 to 119 is that one. And I've got a 120 down here, and I missed a guy. This 105 should have been in this group. That should have been 11. Let's make sure I counted everything. 4 and 3 is 7. A 17 is 24, 25, 35, 36, 37, plus 7 is 44. And I had 1, 2, 3, 4, 5, 6, 7. 1, 2, 3, 4, 5, 6. 6 times 7 is 42, 43, 44. Okay, that's everybody. So when I look at the distribution here, for the shape of the distribution, I'm going to do this fairly quickly. I've got 1, 2, 3, 4, 5, 6, 7. 6, 7. This would be 90, 95, 100, 105, 110, 115, 120. And my highest count is 17. So I'm going to call this 20, 10, 15, 5, and so my first count goes up to 4, and then I have a 3, go up to 17, down to 11, and then 7, and 1 and 1. So, it's not a perfectly bell-shaped distribution, but if we had to smooth this, we could make an argument that it's roughly bell-shaped. This is just sample data. And so let's proceed and let's look at how this relates to the empirical rule. So I'm going to sketch a new bell-shaped, and in the middle, I'm going to label this with the mean for our eruption times. So that's X bar is 104. And the standard deviation is 6. So when I go one standard deviation in either direction, I would either add or subtract 6. So this would be 110. And 104 minus 6 is 98. If I go another standard deviation, I'd add another 6. And one more time, this would be 122. Subtract 6. And again, so those are the markers there. And as far as the percentages, this corresponds to 68, 95, and 99.7. So 68% of the eruptions last between 98 and 110 seconds. 95% of eruptions last between 92 and 116 seconds. And 99.7 lasts between 86 and 122. So what's interesting is if you go back and actually look at the number that fall within this range and compare that. If we had a perfectly bell-shaped distribution, we would get answers that are really close. Now, in this case, our distribution was not perfectly bell-shaped, so we might not get exactly 68%, but these are pretty good estimates. They'll be better the closer your distribution is to a true bell shape. So we're asked what percentage of eruptions last between 92 and 116 seconds. So now it's easy to say that that's 95%. All right, I hope that's helpful. I'll see you next time.